just wanna take you anywhere that you would like. We could go out any day, any night. Baby, I'll take you.
Every single minute, the equivalent of a full garbage truck of plastic enters our oceans. There isn't just an environmental problem anymore. Microplastic have been found in our food, our drinking water, and even inside our human body. So the question is there anything better? Something strong, safe, and natural that we already have access to? Actually, yes. It has been here for over 400 million years.
Here is where cellulose get interesting. Each cellulose chain has hydroxyl groups, OH group, sticking out from the sides. When chains line up next to each other, those OH groups pull on each other through hydrogen bonds. Multiply that by hundreds of parallel chains, and you get a tightly packed crystalline structure called a microfibril. Now that we understand the structure of cellulose, let's explore what makes this one of nature's greatest engineering achievements. First, cellulose has exceptional mechanical strength. The extensive hydrogen bonding between cellulose chains creates a highly stable structure that can support the growth of large plants and trees. Second, cellulose is insoluble in water. Even though plants are constantly exposed to moisture and rain, cellulose remains intact and continues to provide structural support. Another important property is that cellulose is biodegradable. Unlike many synthetic materials, cellulose can be naturally broken down by microorganisms, making it environmentally friendly and reducing long-term waste accumulation. Cellulose is also renewable because it is continuously produced by plants through photosynthesis. As plants grow, they naturally generate more cellulose, making it a sustainable resource for future applications. In fact, cellulose is the most abundant organic polymer on Earth. It is found in plants, cotton, wood, and many other natural materials, making it one of the most important biomolecules for life and sustainable development.
When it comes to the synthesis of cellulose, there are actually 5 synthetic routes: natural plant biosynthesis, bacterial biosynthesis, enzymatic in vitro synthesis, and 2 purely chemical laboratory approaches, which is polycondensation and the stepwise addition method. Ever wonder how plants build cellulose from just glucose? It's the reverse of digestion, and it's all about one molecule of water leaving. 2 glucose units, one has an anomeric carbon at C1, the other has a free OH at C4. To link them, we first need to activate that C1 oxygen. H3O plus protonates the OH at C1. This makes it a great living group. The CO bonds break, water leave, and we are left with an oxocarbonate ion, a stabilized carbocation at C1. Now, the OH at C4 on the second glucose attacks that carbocation, nucleophilic attack, forming the new glycosidic bond. But now the oxygen is positively charged, a base removes the extra proton, deprotonation, and we are neutral again. One water molecule release, one glycosidic bond form. Repeat this thousands of times, glucose after glucose, and you get a long straight chain cellulose. Protonate, leave, attack, deprotonate. That's how plants build the strongest natural fiber on Earth, one bond at a time.
Here's the part that I think it's genuinely exciting. Recent research has shown that we can design new types of cellulose by changing the building blocks before they go into the enzyme.
Instead of regular glucose, scientists use a modified sugar called a fluorinated glucose analog. They fed this into the CDP enzyme, but the enzyme still built
a cellulose chain. But the resulting nanocellulose had completely different surface properties. What this means is that we are no longer limited to the cellulose that nature produced.
By controlling the input, we can engineer the output. We can design cellulose for drug delivery system, for flexible electronic, for nano-composite materials, and for tissue engineering scaffolds. Cellulose isn't just something that we extract from the woods. It's becoming a design platform, a starting point for materials that we haven't built yet.
You probably ate cellulose this morning. Every vegetable, every grain, every fruit. The fiber in your food is mostly cellulose. But cellulose also has a growing role in medicine. When modified chemically, cellulose can form a hydrogel, a three-dimensional mesh structure that human cells can grow on. This is the basis of tissue engineering. Cellulose-based materials are being used as wound dressings that are biocompatible and biodegradable as capsules that carry drugs to a specific location in the body, and as scaffolds that support the growth of replacement tissues in the laboratory. Plastic is made from petroleum, a fossil fuel, and it can take 500 years to break down in the environment. And even then, it leaves behind a microplastic particle that enter a food chain. Cellulose made from plant. Grow using sunlight. When it breaks down, it will return to a soil as a water and carbon dioxide. So there is no residue, no lasting pollution. Cellulose-based materials are already replacing plastics in packaging, food wrapping, by disposable container.
At the start, we ask a very simple question. What if nature already created a better material for us? For over 400 million years, every plant on Earth has been quietly building one of the strongest, lightest, and most sustainable structures ever known. No factory required, no fossil fuels, just the sunlight, water, carbon dioxide, and one remarkable molecule.
Cellulose solved the problem we are now trying to solve. Maybe the future of green chemistry does not begin in a laboratory. Maybe it's begin within a lake.